to identify the other one. I don't know. And I guess she's going to explain us what she's doing, what she's trying to do. So,
Okay.
please.
So thank you. So as you can see from my title, today I'm going to talk more about all about radio. So I will begin. Okay, it stopped working.
Please just remove and do manually. It will be faster and better.
Yeah. No, it's not working. Okay. So I will start by explaining the different types of radio emissions. Then I will talk about the radio emissions from exoplanets and brown dwarfs. And then at the end, I will briefly talk about BHP 0701, which is like a young stellar object I've been working on for the last few months. Okay. So to begin with, here we have different radio images of different objects. But do you think all these radio emissions are same? Are they being emitted by the same mechanism or are they different? Well, broadly, radio emissions can be classified into two types. One is the spectral line emission and the other one is the continuum emission. I won't be talking much about the spectral line emission, but just to have an overview, it is basically connected with the excitations and de-excitations at molecular and atomic level. And the famous example for a spectral line emission is the 21 centimeter line, which is emitted when, in a hydrogen atom, the electron flips its spin to make it antiparallel to that of the proton in order to achieve the lowest energy state. And so talking about the continuum emission, there are two main categories. One is the thermal emission and the other one is a non-thermal emission. Now talking about the thermal emission, it is usually incoherent. Incoherent means that in this case, the particles that are emitting the emission, they are not phase aligned. So they will be emitting at different frequencies. So due to this thing, the incoherent emissions have quite a broad spectrum. But talking about the non-thermal emission, it can either be coherent or incoherent. So first, I will talk about the thermal emission. So as the name suggests, it's a thermal emission. This means it is something that has something to do with the temperature of the objects. So all the objects in the universe, which have a temperature, say above 0 Kelvin, they will have some sort of thermal emission. And the two main categories in thermal emission are the blackbody radiation emission and the bremsstrahlung, or you can say the free emission. Now, most of you might already know that what a blackbody emission is. It is something that is governed by the Planck's law, and it is emitted by objects with respect to their physical temperature. For example, here I'm having a plot of the energy of the emitted flux with the wavelength. And so it is the emission that corresponds to temperature of a body. For example, even all the stars are emitting blackbody emission. And that's why we see some stars are red and some are blue. Why? Because the hotter stars, they emit brightly at the redder end of the spectrum, and the cooler stars, opposite. The hotter stars, they emit brightly at the bluer end of the spectrum, and then the cooler ones, they emit brightly at the redder end of the spectrum. And the most famous examples in the universe, the most uniform blackbody emission, is the cosmic microwave background, which has a thermal spectrum at, say, 2.7 kelvins. Now talking about another kind of thermal emission, it's the bremsstrahlung emission or the free emission. And it is something linked with the thermal motion of the electrons. So when it happens, that when the electrons, they get scattered by ions, but without getting captured by them. So there are some changes in their energy levels, and this is when they emit the bremsstrahlung emission. So this is also a thermal kind of emission, because we know the velocity of the atom electrons depends on their thermal energy also. So that's all about the thermal emissions. Now I will move on to, an example of thermal emission of bremsstrahlung type is something that occurs usually in the ionized gas in the star forming region. So it's pretty common there. So now I will move on to the non-thermal radio emissions, and this is something which we are more interested in, not the thermal ones. So the most typical emission in the incoherent category is the synchrotron emission. So it is basically an emission which is linked with the cyclotron motion of electrons around a magnetic field. So what happens is when electrons, they come in the vicinity of a magnetic field, they start gyrating around it. and start emitting at some frequency, which we call as the cyclotron frequency. But for the synchrotron emission, the electrons are highly energetic. So they are like mostly highly relativistic particles. And this kind of emission is usually polarized. But the synchrotron emission is usually linearly polarized. And as I told you before, it's like quite broadband because it's an incoherent mechanism. And the frequency of the emission is directly dependent on the magnetic field of the source. But it's like not exactly equal to the magnetic field, like it's proportional, but it can also emit like not just at one harmonic level. It can go to like thousands of harmonic levels. So maybe suppose the magnetic field is something around 10 Gauss, and we are having the first harmonic emission at say 20 megahertz, but the system can also emit say at like 40 megahertz or 100 megahertz, which are like multiples of that emission. So the harmonicity can go like to 1000. Now I'm coming back to the coherent emission mechanism, and this is primarily what we are working on. So what is the basic ingredient for a coherent emission to occur? In this, the emitting particles, the electrons, they need to work as a team. So they need to move in unison. So how can we make the electrons go in unison? There are two basic things that can go into this. One is there might be some harmonic oscillation. For example, in plasma, suppose we have a neutral plasma and we have like positive and negative charges there. And somehow a particle gets distorted, and due to the Coulombic forces, they will try to get back to their original position, and it leads to some harmonic oscillations in the plasma. And they are basically moving in unison. And this kind of emission that we get is called plasma emission. But the second case is the gyration, which is similar to the synchrotron frequency emission I talked about, but there's some difference. And this is we call as Electron Cyclotron Maser Instability. And this is the prime mechanism that we are like most interested in. Why? I will tell you in a while. So what is Electron Cyclotron Maser Instability? So for this to happen, you need two prime ingredients. First, you need a source of magnetic field, and then you need a source of ionized plasma or the charged particles. So what happens is that initially the electrons are gyrating around magnetic field and they are emitting some emissions, but at different phases. But if in case there is some external electric field that has a frequency corresponding to that cyclotron frequency, what it can do is it will interact with the electrons that are gyrating. And because of some forces acting there, it will kind of decelerate some electrons and kind of accelerate some electrons. And because of that, they will eventually start getting bunched together. So we will eventually have a phase bunching, and eventually they were emitting, while they were emitting individually in the beginning, they will start emitting together after a certain level of time. And this leads to a coherent emission mechanism, and this is what we call electron cyclotron maser instability. Now, this kind of coherent emission is very bright. And in this one, the frequency is dependent on magnetic field, just like it was dependent on synchrotron emission. But the difference here is like for the coherent emission to occur, the harmonicity, the maximum that you can have is just like 2. So you cannot like say that if I'm having the ECM emission, but the harmonicity is say 100. So it's not possible. So now you have a constraint on your harmonicity that it can either be 1 or 2. So this kind of emission actually works as a very good tool to have an estimate of the magnetic field, if in case you see an emission from a particular source. Because if I'm getting an emission at this frequency, I can have a relationship with the magnetic field. And you can play with the harmonicity like in 1 or 2 and have like an estimate of the magnetic field. Now, these kind of emission have some particular features. I talked earlier that the synchrotron emission is usually linearly polarized. But the incoherent one, for the coherent one, that is ECMI, it is usually circularly polarized. And some cases, it can even be like more than 60 or 65% polarized. And then it occurs for very short time scales. Like it's not something that you can like see for a long period of time. So it might be just a single burst or some burst separated by some intervals of time. And they have like narrow bandwidth, because I told you the frequency is like very like constrained in this one. So it's usually like spikes. Now, if I talk about the emission, radio emission in the solar system, there are different objects that are emitting at radio. For example, Saturn is emitting, Uranus is emitting, Neptune is emitting. and Jupiter is emitting. But there is a thing here that Earth's atmosphere has an ionospheric cutoff of 10 megahertz, which implies that all the radio signals that have a frequency less than 10 megahertz, they won't be able to make their way through that atmosphere. So we won't be able to detect them with the Earth-based radio telescopes. So the only emissions that we can see on Earth with the telescopes like VLA or GMRT or even LOFAR are the ones that have frequency greater than 10 megahertz. And in that domain, only Jupiter falls there. And because of that, Jupiter actually acts as a benchmark reference when we have to talk about the radio emissions from planets or even exoplanets. So here it's like a UV image of different emissions mechanism happening on Jupiter. So Jupiter emits light because of multiple reasons. It emits because of the interaction of its magnetosphere with the stellar wind, which is like very mild. Then it emits because of its interaction with its satellites like Ganymede and Io. For example, here are like different emissions that in the radio that we can see from Jupiter. But amongst all these kind of emissions, the most strong ones are the ones that occur because of the interaction between Jupiter's magnetosphere and Io. So Io is basically a very volcanically active satellite of Jupiter. So what is happening is like Io is gradually imparting Jupiter with a source of plasma. So Jupiter has like a flux tube around it. And when Io moves in that flux tube, it acts as an obstacle. And now Jupiter has a high magnetic field. So there occurs kind of a magnetic reconnection between these two sources. And there occurs a current system. So current starts generating in this system. And eventually, because of that current and everything that is happening, the charged particles in the flux, they get trapped. So once they get trapped, they start emitting coherently. And this is how we can like get ECMI emission from Jupiter. And it's very strong. And sometimes the same kind of thing can also happen in stellar systems, where the role of Jupiter is basically played by a star, and that of the Io is usually played by a planet. So here is basically a brief overview of what is happening for the radio emission from exoplanets or say planets. So as I told you before, you need two prime ingredients: charged particles and magnetic field. Now there are four possible scenarios. First, for the planet, it can either be magnetized or it can be unmagnetized, just like Io, because Io is unmagnetized. Or if it's magnetized, it will be the case of Ganymede. And the source of plasma's energy, that is, sorry, the stellar wind density, or you can say the source of plasma, it can also be magnetized or it can also be unmagnetized. So what are the possible scenarios? In case the planet is magnetized and the stellar wind is also magnetized, in that case, the energy that we need for the ECMI to occur, it will come from the magnetic energy of the interplanetary magnetic field. And if in case the planet is magnetized, but the stellar wind is not magnetized, in that case, the energy required for ECMI will come from the kinetic energy of those charged particles. The other case is if the planet is unmagnetized, and the stellar wind is magnetized. In that case, this will basically correspond to the emission mechanism as seen in Jupiter and Io. But if in case both the planet and the plasma is unmagnetized, in that case, we usually don't see a very strong emission. So these are the four possible scenarios. And apart from exoplanets, what we are also working on is the radio emission from isolated brown dwarfs. So how do they emit is, like brown dwarfs also have like, you can say, a shell of plasma around them. And so when they like rotate fast, the currents are generated in that plasma region around that, along the surface. But if we go to some further distances from the surface, there is some instability in that current regions also. And because of that, there is some instability occurs there. And again, we get like the trapping of electrons and all that stuff. And when they interact with the magnetic field of the brown dwarf itself, it can again lead to ECMI emission. And the other case is that maybe just like Jupiter, even an isolated brown dwarf can be orbited by a small satellite. So in that case, such kind of interaction is possible. And then also we can see some emission from brown dwarfs. Now, why brown dwarfs are important? Well, the first thing is that brown dwarfs have magnetic field of the order of kilogauss. which is very high compared to the magnetic field of planets, which is just like few Gauss. So, and also in the past, there have been some confirmed detections of radio emission from brown dwarfs. So we are interested in probing their behavior to a further extent. Secondly, brown dwarfs have a mass ranging in between that of planets and stars. And we very well know, like we kind of know the magnetic behavior of brown dwarfs, and we can and also like kind of know, not very well know the magnetic behavior of stars and also planets. So studying brown dwarfs with radio can actually act as a bridge to link the magnetic field of the lower mass objects like planets with that of the higher mass objects like stars. So we are also interested in studying brown dwarfs. So what is our basic aim? We are trying to construct a link between the exoplanetary magnetism and the better known brown dwarf one. Secondly, to do so, what we are doing is that we propose different observations with different telescopes like GMRT, VLA at present, but maybe in future we will also extend ourselves to LOFAR and VLA, but that is for future. Now, how do we select our planets? Like brown dwarfs, I'm not here talking about the brown dwarf selection, but for the planet selection. Like, because there are multiple stellar systems available in the universe. So which one should we focus at? The first thing is that we are basically focusing on planets which are like more than 5 Jupiter masses. Secondly, we, as a non-phenomena, the magnetic field is known to decay with age. So as a stellar system ages, the magnetic field is expected to decay. So we are mainly focusing on those systems which are quite young, that is like say less than 1 giga-years old. And also an emitted flux from a system, it will decay as an inverse square of the distance between us and the system. And because of that, we are constraining ourselves to nearby systems that is like less than 50 parsecs away. And this, following all these criteria, this list has been compiled by a student, Rebecca. She's doing her master thesis with us. So we have like a list of more than 100 possible systems that we can look into. But this is just like a preliminary list. Further, what we need to do is we need to see, because whenever you apply for proposals, you need to give a flux estimate, or that, okay, from the system, we are expecting this much flux. So we want this much sensitivity. So how can we estimate that flux values? Well, to do so, there are some scaling laws, but the thing is that these scaling laws are mainly based on the observations of planets in our solar system, like mostly Jupiter. So they might not give very correct estimates for exoplanets, but at the time being, this is the best shot that we can do. So these scaling laws, they relate the emitted radio power with different parameters, like the stellar wind velocity, wind density, the velocity of the particles, and all those things. And in this thing also, this stellar wind velocity and wind density and their age and everything, these parameters are not very well constrained for all the systems. So what we are doing is, we are basically defining a range of all these parameters, like in this graph. So what we do, that whenever we have to make estimates for a target, we define a range that, okay, maybe for this system, the stellar wind velocity will lie in this to this value, and the density will lie in this to this value. And then we play around those parameters to have an estimate of the flux. Like this also we did for one of the targets, like this is the graph that we obtained, like all these values. And that blue region was something that we could focus on. So if in case we are lucky to have a detection, we can also use our estimated flux to better constrain these values also, to some extent. Not very accurately, but yeah, to some extent. And in the last year, we have made, I guess, around 4 to 5 proposals. Some of them have already been observed, and some of them are scheduled for observation in the future, say in June. And we are working on the data analysis. But for this system, the one that was observed for the first time in 2021, I guess, this was also like a massive substellar object. And for this, we have now obtained some upper limits. The thing is, for this system, there was a very bright source in the field of view when we were observing, around like more than 200 millijansky strong. So because of that, we couldn't reach the sensitivity that we were aiming to reach. So the RMS for this one was around 0.15 millijansky. So this means the upper limit that we put on it is around 0.45 millijansky, which means that if we want to detect this target with this instrument again, it has to be stronger than 0.45 to have like a confirmed detection case. Apart from this, we submitted other proposals targeting some brown dwarfs and again some exoplanets and also some samples from Carmenes and also to VLA. So just like a summary of all the projects that we have done so far. Okay, so now I come to the last part of my presentation, that is BHP 0701. Now, what is BHP 0701? So it is basically a very young stellar object of spectral type K7, and it is located in Barnard 59, which is like a very active star forming region in Pipe Nebula around 163 parsecs away. And this is also a pretty young system, having an age between 1 to 5 million years. But why is this system so special? Well, in the last few years, there have been some observations of the system with VLA and ALMA. For example, in 2020, they observed the system with ALMA at 226 gigahertz and with VLA at 22 gigahertz. And what they saw was that they were seeing a clear emission at the center, at the position of the star, but there was also a disk around it, just like this big disk. But this disk was like not very constant. There was some gap in the disk, and that gap, like these gaps like this, and they were like almost 107 astronomical units wide. So that was the first thing that they saw, that there was a disk. The disk was 107 AU strong, so wide, and then there was a 70 AU gap in between, standard at 50 AU. But okay, having a gap in a disk is fine, that it happens. But what they saw was that with VLA, even in that gap, they saw a second detection, a second signal. So it was possible that maybe it's having some companion, possibly. But the thing is, this was not seen with ALMA. ALMA only saw the CO signal at the center, at the position of the star, but not in the gap. But with VLA, it saw a detection of almost 30 microjansky signal at the position of the gap also. So this observation was followed up later with VLT, and there also they did it like with different filters, but with the they saw that second object just in one observation. With this one, for example, this is an observation at different band, say H band. There, this yellow region is the one that is CO emission that was detected by ALMA, and then this is the signal that was detected by a VLT. But at the other band, they could also see that along with the central signal, there was also another signal at the position of the gap. So this again, like hinted that maybe the second object is still there, and it might be there, but still this could not be detected, because why are we only detecting in just one band, and why is ALMA not picking it up? So now what we are doing is, like, I am working on the same object, but with VLT data at another frequency band. So it's like now I'm working on KU band, which is between 12 to 18 gigahertz. And so basically, we have like 8 observations of this data, and I was analyzing their data. And here I have combined, these images are from Stokes I and Stokes V. So what is Stokes I and Stokes V for the first thing? So Stokes I basically gives the entire intensity of the signal, like over the entire polarization domain, like maybe linear, circular, everything will be covered up in Stokes I. But Stokes V, it only gives the intensity of the emission, which is circularly polarized. So when we compiled all the data together, we found a clear detection in both of them, even in Stokes I and even in Stokes V. But the thing was, when we tried to see these images individually, like for different days, we saw the Stokes I detection on all the observations. But Stokes V was only clear for these 2 days, March 5th and March 26th. So Stokes V was there, but only in first day and the other day. And for the other days, there was like no Stokes V detection. And also the first data is not something that we can fully trust, because there were some observational errors in this one. But still, if we talk about the 26th March data, even if we talk about the signal, it's 33.5% polarized. And it was almost an 8 sigma detection. So this is not something that we can ignore. It's saying it took a systematic error. So now there are some open questions that, okay. So seeing this variation, we like kind of plotted the flux of the source on different days. So we were like kind of seeing some behavior, like the flux was changing, it was increasing and decreasing in Stokes I and also in Stokes V. Well, for Stokes we just had two detections, so we put like the 3 sigma upper limits to see how it might vary. So seeing this variation, we thought that maybe if we try to do this time series also for individual days, we might see some pattern in that also. But when we try to do that, we had different time series, but they were not following a clear pattern. So we were not having a specific period. And even the when we try to do the power spectrum thing, the period that we got was extremely different for all the different days. And that also with high false alarm probability. So still, we cannot trust if this signal is following a proper periodic behavior or if it's just random disturbance. So there are some open questions like what is causing this coherent emission? Because earlier the claims were that maybe that emission from the second source is also, or from the star, is coming because of the free mechanism, because that is like the most common for the young stellar objects, like the free emission mechanism, the thermal emission. But if it was free emission, it should not have been polarized. But what we are seeing is polarized. So what is causing that? So there are like two possible reasons for that. They're just like possible, like there can be multiple reasons. First thing is that maybe the star is flaring. So if it's causing flare, so maybe we are having some coherent plasma emission from the surface. That is one possibility. And secondly, maybe it's having some magnetic interaction with the earlier proposed companion. So maybe that companion is there and we have not been able to detect it, but it's causing some interaction between those two objects, and that is why we are getting that coherent emission. But again, the question is, if it's there, why it's only there in just 1 or 2 days? Why isn't it there every day? So maybe it has something to do with the phase of that object or something, but it's still not very clear. Or maybe something we don't know about at all. Not an alien, but maybe something that we are not sure about anything. So what is our next step? So we will now try to play more with this data. Like now we will try to like subtract the visibility of the source, because the central source is very bright. It was around like 150 microjensky or like 160 microjensky. And the second signal that we saw in Stokes V was just like 30 microjensky. So what we'll try to do is, so maybe in the other days also that emission was there, but it was weaker and we were not able to detect it. So what we will do now is that we will try to use the data and subtract the visibilities of the central source from that and see if we see a second peak there or not. So that's all for now. Yeah, thank you.
Questions? Comments?
Very nice talk, Simran. About the flaring hypothesis here, did you think about having some photometric monitoring to see if there's, so flares are not the reason, it would be coronal mass ejections, right? So you have a flare,
yeah, maybe,
and then particles being emitted and then being causing this emission. But do you think some monitoring photometrically would help there?
right now we are just working in radio, but maybe in the future, like when we are like a more iterative analysis, maybe it can be proposed for future observations. So
That would be a way to at least to know
Yeah.
whether this happens often or not, because if it happens quite often, then it's not impossible you caught one of these events actually.
yeah, actually, because right now we're just having just 8 observations, and they were also like separated by different days. So we are not sure if maybe it was having a periodicity in that also. Maybe we missed that day. So we can do this maybe in future.
That's maybe a data already.
Yeah, it might be that.
Okay.
Yeah,
Sorry, very nice, thank you. Just a question, you mentioned that this might be coherent emission. Why it's coherent? Because of the temperature? How do you know that it's regular coherent?
Because it's polarized, and usually the polarized ones are the coherent. There is like a possibility.
Polarization.
Sorry?
This, but they're circularly polarized
Yeah, it's circularly polarized.
a bit. I mean, there are no coherent emission that are circularly polarized.
But usually the ECMI, it is not yet.
No, if it's.
No. So that is a possibility. Because there's also like a coherent free emission also that might be possible. But right now we are like still figuring out maybe. So if a second system is there, then there's a strong case of the interaction taking place between them. So we are like kind of working on that domain, but yeah, we will see all the possibilities.
Thank you. Very nice introduction and very nice presentation. About the secondary scenario, if there's a Kuband, can you exclude that this is a low mass star?
Yeah, like with the VLT observations, they have put the mass of that companion to be around 4 to 70 Jupiter masses. So yeah, it might, so the mass has been like not well constrained, but they have like put a limit on that.
And do you know the nature of the disk? What is the source of this from the object?
The thing is that the star is it's still in the process of forming. So maybe it's the one from the beginning itself. And if in case the second object is confirmed, it might actually confirm the case of a simultaneous star and planet or star and brown dwarf formation. Because it's a very young stellar object, still in the process of forming. So it's from the beginning of
Yeah.
Yeah, thanks for a very nice presentation. You explained the mechanisms of nation.
Sorry?
That you explained at the beginning the
Yeah.
the mechanisms
Mhm.
of nation. Can you briefly explain why you get circularization in one thing?
For the ECMI.
Yes.
Yeah, because they are kind of gyrating in bunches. Like for example, for the linear polarization, if we see, it was like the electric field and the other one was like perpendicular. But in that case, they're like following a particular motion in just one direction. So the electric field will be like aligned in that direction, kind of, if I'm making it clear. So it's kind of there. I'm not being able to explain it properly.
Let's check what we have on Zoom.
No,
Nothing.
no. It's nothing.
Okay, then let's finish. Thank you.